Okay, so we will get started for today's lecture. So we'll talk about thermochemistry, and some of you may have already learned that. So thermodynamics. So in chapter 6, so there are 3 chapters are related to thermodynamics. Okay, so chapter 6, where we talk about the change of state of your substance. So you can go from solid to liquid to gas. That is thermodynamics, but we learn about the concept of enthalpy. So today we will be talking about entropy and several laws of thermodynamics. So the 0th law, okay, this is not the 3 laws that we will be discussing today, but the 0th law. Take a minute to read through these statements. Okay, so actually Maxwell, in a few years later, he makes it much simpler. It's talking about thermal equilibrium. Okay, so this is a very basic definitions. So think about what is temperature. So how would you define temperature? You can write down a sentence or just think about it in your mind. What is temperature? You can use a thermometer to measure temperature. How does thermometer work? It's based on the change of its volume, right? The height of this is probably a alcohol-based thermometer. When you change the temperature of your surrounding, the height of this red stuff is different. So the traditional thermometers are based on mercury, but the alcohols one also work, and these are just delicately designed and calibrated system. It look at the change of the surrounding temperature and how it affects the pressure inside. From this, we know the pressure has to do with the density and the height of liquid. So you see how all these things are connected together. And I don't know how many of you watch Game of Thrones, right? In the winter time, you feel cold. When you hold a cup of coffee, you feel warm, right? So let's go back to the 0th law. So when you actually are feeling the cold or the hot, that means there is an energy exchange between you and surrounding. So in this chapter, we'll be talking a lot of stuff about surrounding and your system. So system is something you're observing, okay? So I feel cold is I'm observing myself. I feel the heat transfer from me, the body, or the system to the surrounding. Max Planck basically state that if A is the same as B and C, then there's no energy transfer between each system. That makes sense? So what is thermodynamics? It is a study of how the energy flow from one part to another part. Okay, so you're thinking about heating up a cup of water. You have to put energy in so that the temperature will change. If you want a cup of hot coffee to become cold, you can let it sit outside, right? The surrounding temperature is lower than your cup of coffee, so the temperature will gradually decrease. The energy will flow from the higher temperature, which is the coffee, to the lower energy place, which is surrounding, right? They want to share the energy so everybody have same amount of temperature or the movement of particles, right? Okay, so like I mentioned, chapter 6, if you do not remember what's going on in chapter 6, I would encourage you to go back to read that chapter. And then chapter 20 is what we'll be discussing now. And then we'll go back to 21, where we can relate electrochemistry to thermodynamics. Okay, so if we think about thermodynamics, you can think about how I can pick up a book. So I put energy into that book and let it drop, right? The gravity will pull it down. The potential energy is converted into kinetic energy. So in thermodynamics, we're concerned about the work and heat you do to the system. So think about gas expansion. We know PV equal to nRT, right? So if I increase the temperature, if the volume is fixed, if I increase the temperature, someone figured out this equation, but we memorize it basically. When you see an increase in temperature, you get an increase in pressure, right? Why? Okay, so thermodynamics explained it. If you think about if we have a reaction happening in a closed container, right? When your number of gas increases, you will get what? Increase in pressure. So we'll discuss it in a little bit. So potential energy of a system, sometimes you will see U, sometimes you will see E, is equal to the heat and the work you do to the system. Let's say the volume is not fixed. You have a piston. If the temperature increase, right, the volume increase, it does work to the surrounding. That makes sense? So you think about combustion of your engine. When you burn the fuel, you get a rapid increase in the volume of gas, and that do work that drive your car. Okay? So again, the most important concept is that when you do these calculations, you always do final minus initial. You've probably already seen that in many calculations. Okay, so when we're considering a system, when the delta E is less than 0, that means you're releasing that energy to the surrounding. So same for the delta E is larger than 0, that means you're absorbing heat from the surrounding. Okay, so let's look at the first law of thermodynamics. So honestly, I don't need you to memorize what these laws, like what is the first law and what is second law, but you have to remember the content inside of these thermodynamic law, right? You will be using these concepts over and over many fields in chemistry. So first law basically is the conservation of energy. I'm sure you learned that before. So energy cannot be created or destructed. So that means your total energy of the surrounding and the system is constant. So let's look at the unit of energy. Okay, it's usually you use joule, right? So it's in honor of someone that invented this concept. Joule, you can think of a work that you've done to the system. So how do we define work? It's basically force times distance, right? So if we look at the unit, the force, F equal to ma, I'm sure you learned that from physics. If you put these units together, that's how you get joule. So when you're thinking about force, let's think about we're stretching a chemical bond, right? We need to put work into it. So we use angstrom when we're stretching a chemical bond. We need to put work in it, so the bond length will become longer and longer, right? In that sense, you can think of chemical bond being stretched, the bond become weaker because part of that energy is what you put into the system, okay? So if you take derivatives, if you look at the step, you can get force from such curve. That makes sense? So that's where joule is coming from. So a lot of time you will hear calorie, right? So if you think about the food you eat is measured in calories, so it's basically a unit conversion. You will also hear about BTU, which we won't discuss further. It's just another unit that British use. So one thing you have to be careful is that when we're talking about heat capacity or when we talk about heat, we usually use kilojoule. But for entropy that we'll be discussing today is in joule. Okay, so you have to watch the unit. It's very important. In chapter 6, we talk about state function and how it's independent to the path. So think about a cup of water. The cup of water that is 60 degrees, if you heat it from 0 to 60, the amount of energy in this water is equivalent to a cup of water that is being cooled from 100 to 60 degrees. So it doesn't matter how you get there. The heat capacity that you learn define how much energy is in such system. So that basically summarizes the first part. And we talk about PV equal to nRT, how it can do work when you have a volume change. So if you think about the Haber process, the number of mole of gas decreases. What does that mean? Your pressure will drop, right? So that means you need to put additional energy into such system for this reaction to work. So we'll come back to that in a little bit. So what's enthalpy? We can simply think of it as heat. So enthalpy is heat, delta H. In chapter 6, you calculate delta H of a reaction, and then you can do the Hess equation. If you do not remember what that is, I will recommend you go back and look it up. So you can use the Hess equation to calculate how much energy is involved in a chemical process. So basically, you think about how much energy is stored in a chemical bond and how much energy it takes to form these bonds. And the surplus of the energy is determined whether a reaction is endothermic and exothermic. So if we are at constant pressure, it's a very big assumption that you could make. You can basically take away that term, so where your delta H is delta E. So that's why in high school, a lot of process, if you think it's exothermic, which is mean release heat to the surrounding, you would generally think this reaction is feasible. But however, there are some processes that is endothermic, but it's still thermodynamic favored. Okay, so this is contradictory to each other because generally heat of reaction cannot determine whether a process is spontaneous or not. Okay, so heat transfer is very important in a lot of processes, especially in chemical engineering. That's all they do. They deal with thermodynamics, calculate how much heat you can use. So if you think about desalination or the harvest of salt from seawater, right? So generally, they have multiple reactors. So of course, the pressure is different in these reactors, right? So they can reduce the temperature, and what would you get? Reduction in the boiling point of water, right? So you can more effectively to evaporate the water, so remove the water from such system. So the water molecule is gaining entropies. Okay, so let's think about phase change. So usually when we have a cup of ice water, the water contains ice cube. When we calculate in the heat capacity, we have to separate these two terms out, right? How much heat can be absorbed by water and how much heat can be absorbed by ice cube? There are two different values, right? Why? Have you ever thought about why? Now I want to talk about how these values are measured. There is a thing called the calorimetry. So it measures how much heat is released to the surrounding. So when we think about the heat capacity, it's usually in mole, right? How much energy I need to put into a mole of substance for it to increase temperature by 1 Kelvin or 1 degree C. So you have to think about freedom of particle motion, right? So in gas phase, you have a lot of kinetic energy, right? At lower temperature, from the kinetic theory of gases, the kinetic energy decreases. So think about why. Why does it decrease when the temperature drops? So you can go back to this equation, right? It makes sense. Where is pressure coming from? It's the force exerting by the gases to the wall of your container, right? So when you lower the temperature, they move slower, so you have lower pressure. So we kind of just memorize that, but thermodynamics explains the origin of these phenomena. So you can think of a cup of water versus ice. The degree of freedom in liquid water is much higher than that of ice cube. So this is the calorimetry, okay? So it's a sealed container. We can assume that the heat loss from such system is minimal. So we can put some amount of your substance that you want to analyze into your sample, and we can ignite it with a spark. Then we can measure the temperature change. And in such case, we assume there's no energy loss from such combustion and reaction. So we can, using the heat capacity of water, to quantify how much energy is released from the combustion reaction. But of course, you have to consider when the water temperature increases, the stirrer also takes away some energy. When we think about a closed system, you have to consider all the components inside. So this is definition. Specific heat capacity is basically the Q, which is the heat that you put in, then divide by mass and temperature. Okay, let's look at the second law. The second law basically states that all the real process occurs spontaneously in the direction that increase entropy. So increasing entropy is good. If we have a decrease of entropy, think about the synthesis of ammonia, you decrease the amount or the number of mole of gases, right? So that means you have to do work to such system, or there has to be some energy gain from such process so that this reaction becomes feasible. How would we define entropy, the delta S? Okay, you will see that you didn't see this before, but it basically is a measure of how random or how disordered a system can be. When we think about disorder, you should think about gas or a boiling water versus ice cold water. The degree of freedom of water molecule are different. Let's think about SO2 and SO3. Which one would have higher degree of freedom? If you draw out the structure, this is a linear molecule, and this is a triagonal molecule, right? So for sulfur dioxide, there's multiple options, right? Imagine sulfur is in the middle, and then the oxygen atom, it can move out and bend in, right? And another scenario is one come in and the other one go out. The bond lengths, they can continuously change. But think about SO3. It had 3 oxygen. So you have more scenarios of such process can happen, right? 3 of the oxygen can come in and out, or 2 of them can come in and out, and with 1 oxygen doesn't move. And then the third scenario is where 2 of the oxygen atom doesn't move, and you have 1 oxygen moving in and out, okay? So degree of freedom can also be predicted. So delta S is defined by this equation where when you have a reversible process, you may be confused what is reversible process. So reversible process means when this system can be reversed given enough energy. So for reversible process, that heat or that energy involved in such system, delta S quantify its relations to the temperature. Okay, so you will get a unit of joule per Kelvin. Okay, so there's also a Boltzmann equation that's stated where S equal to K and natural log of W. So W here is not work. Okay, W here is the number of microstates. So that may be a little bit confusing, but I'll explain it later. Think about when you have only 1 microstate, a perfect crystal. If W equal to 1, your natural log of 1 would be 0, right? That means you have no entropy, 0 entropy. So when you have a lower S, you have fewer microstates. Microstates is basically if you take a snapshot of your system, where the molecule is. So you can use statistical mechanics to calculate the probability of you finding the particle, right? So we know gases, they are far apart from each other. So when you take multiple snapshots, you may not see your particle or your gas particle at a certain spot, right? Because they just randomly move around. So when for a higher S, that means you have more microstates. So I will refer to figure 20.4 and figure 20.7, okay? So figure 20.4 basically is an example of microstates. So let's say these 2 containers are connected, right? But we have a gate that limited the gas molecule to 1 compartment. If I remove this gate, we have one scenario where 2 particles is located in the compartment A, and this is called compartment B. So another scenario is each of the compartment will contain 1 particle. And another scenario is 2 will have is located in the B compartment, the B location. Then you can imagine where you have many of these atoms or gas particles inside the compartment, right? You have many possibilities. So S is basically a measure of probability or the randomness of these particles. Okay, so we already discussed this example, the ice versus liquid water. We can think of combustion of gasoline. So you converting a fuel, let's say a very simple fuel, methane, right? CH4, it can react with oxygen and generating what? CO2. Let's think about dissolution of salt in liquids. Ionic salt can dissociate, right? So sodium chloride, it becomes sodium ions and chloride anions, and that is solved by water. So the degree of freedom increase rapidly. When we think about oversaturated solution of sodium chloride, that means such system has so much free sodium and free chloride to an extent that it becomes energetically unfavorable to dissolve more salt. Okay, and then we can remember an experiment that you observed last semester. The crystallization of salt can generate heat. So I think it was sodium acetate. So you go from a very free form, fully dissociated sodium and acetate, and when you crystallize, you become solid, you have to release that excess energy in the form of heat. So that is a conversion of your entropy to enthalpy. Okay, so how about dissolving gas in liquid? You're decreasing the amount of entropy of your gas, right? So that's why in the summertime, the natural water, like the river, the fish will die because there's not enough dissolved oxygen due to the temperature increase. When the temperature increase, you get more entropy, right? The gas will want to go somewhere they're more happy, which is surrounding that. So escape from the water. I hope that makes sense. Okay, so let's look at the third law. The third law stated that a perfect crystal has 0 entropy, so it doesn't move. However, that's not the case. So for those who are studying electrophysics, you will later learn that there's no such thing called perfect crystal. So every system will have residual entropy, but we won't go further because this is general chemistry. So the assumption is that a perfect crystal, it doesn't have any movement. So you think about a very hard, solid, it doesn't have movement, but at room temperature, they still have some degree of freedom. Okay, so they are vibrating at certain frequency because the surrounding is below 0K, it has energy to move. Okay, so this is a more complicated statement. Take a minute to read through it. Okay, so we already discussed this. So when we are talking about standard entropy, we're talking about a standard condition, right? Standard condition is 1 molar and 1 atm for gas. And previously, we briefly mentioned this equation. So if you remember Van Hoff equation, so we briefly utilized this equation to derive such equation. Okay, so for the standard change in enthalpy, you will see the little circle. That means it's a standard condition that we're talking about. It will have a unit of joule per mole per Kelvin. So again, final minus initial, that's a very important. When you're calculating the change in the entropy of your system, you always do this, okay? So this is the same as when you calculate heat of formation, you calculate the final energy of your compound and minus your reactant. When entropy is larger than 0, that means entropy increase, that means it's more random, right? So one case is where you have higher temperature or you have more particles, more number of mole of gas forming during the reaction. Then your delta S is larger than 0. So we talk about the Haber process. With the synthesis of ammonia, you decrease the amount of number of gas during the ammonia synthesis, right? You're converting nitrogen and 3 hydrogen into one ammonia molecule. That's why delta S will be negative. You're decreasing the entropy. So that should be simple. So however, we cannot predict sign of entropy unless we are talking number of mole of gas. You can think about a system where let's think about a strained molecule, cyclopropane. Okay, so you can heat it and it can undergo rearrangement reaction and you will get such molecule. So in a ring, it has less degree of freedom because they're restricted. They're connected to another carbon, right? But when the ring is opened up, it has more degree of freedom, okay? So let's look at an example. Okay, so this complicated ring molecule. So under certain condition, it can undergo polymerization. You can think of it as the S8 molecule, the sulfur that we previously done an experiment on. We heated the sulfur, it becomes this rubbery and plastic due to the connection of multiple sulfur atoms. So in this siloxane compound, under certain condition, we can get a polymer called silicone. This process is driven by the increase in the flexibility. When it's present as a ring molecule, its degree of freedom is limited, but when you become a polymer, a siloxane, silicone molecule, you have more freedom, right? You can have more microstates. So such process is feasible because we know thermodynamics tell us for any system, if you have an increase in your degree of freedom, this process is favored. Okay, so let's talk about your system and your surrounding. So when you give off heat, the heat had to go somewhere. So it goes to your surrounding. So constant pressure is a very big assumption that we made before. At constant pressure, your heat is equal to enthalpy. But when it's not constant, that means there is expansion of gas. It does work, right? So then such system, you have to consider both heat and the work that it did due to expansion. So I want to differentiate these two words, spontaneous versus instantaneous. So for a spontaneous chemical system, it doesn't mean it will occur instantaneous, right? So let's think about we mix methane with oxygen. Unless you use a spark to trigger such a reaction where it generates enough heat to trigger the next combustion experiment or process, it's safe to mix methane with oxygen. The reaction doesn't happen, right? So during the combustion process, we call that a self-sustained process because your product from such reaction process, it generates heat. And that heat is high enough to trigger the next combustion reaction. So being spontaneous doesn't mean the reaction will happen on its own. Since the energy cannot be destroyed, it has to go somewhere. So we will put the negative sign to our system calculation. So the heat has to go to the surrounding. So when we go back to the second law basically says that entropy of your system, a decrease in entropy of your system, that decrease is generally less than the increase of your entropy of your surrounding. And then most importantly, the entropy of the universe is always increases. Okay, so that's another pretty important concept in thermodynamics. So finally, let's talk about delta G. So for any reaction, we can calculate its Gibbs free energy. It's stated by this delta G. Okay, when you see a zero up here, a circle up here, that means under standard condition. Okay, so you have to consider the delta H, which is heat from such process, and a temperature dependent term of your delta S. Because remember, the unit of delta S is joule per Kelvin, right? If you times the temperature, that will give you the same unit that you can keep calculating the energy of your system. So generally, when delta G is less than 0, we will say this process is spontaneous, it's energetically favored. That's why a lot of time when you see an exothermic reaction, you generally would think, oh, it could be a spontaneous reaction, it happened on its own. Because we assume constant pressure. We assume this term have minimal influence on your system. So if we're going back to the polymerization process, in such system, the increase in entropy is what drives the reaction. So in some field, you will hear about entropy-driven ring opening reaction. This is one example, and there are many other examples. So that's all I have for today. So do you guys have any questions about all the concepts we discussed today?